Physics in motion. Physics in motion.
All right, buckle up, physics fanatics. Welcome to Physics in Motion, the deep dive where we try to make sense of some complex stuff.
That's the plan. Today we're revisiting motion and energy. Think of it like sharpening your understanding of all the forces happening around you.
Yeah, why things move, why they stop, all that good stuff. We're actually digging into the ICP-COJJ textbook for this one.
Our mission basically is to pull out the key ideas, momentum, energy, and make them, well, clear and engaging. Maybe even connect them to things you see in, like, movies or games.
Without getting totally bogged down in equations, hopefully.
Exactly. We want those aha moments.
Okay, let's jump right in. First up, momentum. The textbook defines it pretty simply, right? It's just mass times velocity, P equals mv.
P equals mv. And crucially, it's a vector. Direction really matters.
Okay, so direction matters. To make that intuitive, think about a bowling ball versus a ping pong ball.
Yeah.
Both are just rolling along at, say, 5 miles per hour. Which one do you not want to step in front of?
Definitely the bowling ball. It's got so much more mass. Even at that slow speed, its momentum is way, way higher.
It's like stopping a charging. Well, maybe not a rhino, but something heavy.
Yeah, versus maybe a rolling tumbleweed. Much less momentum.
Okay, so mass is key. What about velocity? Let's say 2 identical bowling balls. One's just rolling, the other's like really moving fast.
The faster one obviously has more momentum, same mass, but double the velocity means double the momentum. It's harder to stop.
So momentum depends on both how much stuff is moving and how fast it's moving. Makes sense. And the units are kilogram meters per second.
Kilogram meters per second, kg ohms. Yep. Okay.
So things have momentum. Why is this such a big deal? Why do we care?
Well, momentum is really the concept that helps us understand how objects influence each other when they, interact, especially when they collide.
Ah, collisions, like in video games.
Exactly. Or pool balls or cars. It connects straight back to Newton's first law, too. An object's velocity only changes if a force acts on it.
Right, inertia. Things keep doing what they're doing.
And to change its momentum, you need that force applied over a certain amount of time. Which brings us neatly to impulse.
Impulse. Okay, the textbook says JLF15, force times time. Also a vector, pointing the same way as the force.
And here's the cool part. The units for impulse are Newton seconds, news.
Which you mentioned are actually the same as momentum units, kg ohms. How does that work?
It seems weird, but if you break down a Newton kg ohms and multiply by seconds, you get kg ohms. It's the same thing.
Wow, okay. Physics is sneaky.
It is, and this connection is super important. It's the impulse momentum theorem. Impulse equals the change in momentum, Ju, or FTC. So force times time equals the change in mass times velocity.
Precisely. It means you can get the same change in momentum with a big force for a short time or a smaller force for a longer time.
That sounds practical, like jumping off something. A porch, maybe, if you land with locked knees.
Oof, yeah. Bad idea. Your momentum goes from downwards to 0 almost instantly. Very short time.
So same change in momentum, but tiny time means huge force. Huge force, that's what jars you. But if you bend your knees when you land...
Ah, like a ninja. Or maybe just someone who doesn't want broken ankles.
Exactly. You increase the time it takes to stop. Same change in momentum overall, but stretched over more time.
Which means the force is much smaller. Let's use the book's numbers. A 100-kilogram person hitting the ground at 7.0 meters. If they stop stiff-legged in, say, 0.05 seconds.
Crunching those numbers, FTT equals A0.05 equals 100 times 7. The force is, 14,000 newtons. That's a lot.
Ouch. But if they bend their knees, maybe stop over 0.50 seconds, 10 times longer.
Then the force is 14,000 divided by 10, only 1,400 newtons. Much, much more manageable.
You see, physics saves the day. And this isn't just for jumping. This is why we have padding in shoes, right?
And helmets and airbags in cars, those crumple zones that are designed to collapse.
Oh yeah, crumple zones, they increase the time of the impact.
Exactly. Even those big barrels of sand or water you sometimes see on highways, they're all designed to increase the collision time and therefore decrease the force. Safety engineering in action.
Okay, let's switch gears. Baseball. Textbook example. 0.15 kilogram ball comes in at 40 meters, gets shit straight back at minus 40 meters. What's the impulse from the bat?
Okay, so the change in velocity is final minus initial. That's minus 40 meters minus 40 meters, which is negative 80 meters.
Got it. So impulse is mass times that change. 0.15 kilogram times negative 80 meters.
Yep, that gives you minus 12 kilograms. The negative just means the impulse is in the opposite direction to the ball's initial motion.
Makes sense. Now, if the bat and ball were only touching for like 0.000000 seconds super fast, what's the average force?
We use impulse force x, so force is impulse time. That's negative 12 divided by 0.000080.
That sounds like a big number.
It is. It comes out to negative 15,000 newtons. 15,000.
Whoa. No wonder hitting a baseball feels like hitting something solid. And the acceleration.
Well, so F is m. That's negative 15,000 n divided by the ball's mass, 0.15 kilograms.
Which is?
A mind-boggling negative 100,000 meters more. That's some serious acceleration.
Insane. Okay, so impulse changes momentum. But what about the total momentum? Is there a rule for that?
Absolutely. That's the law of conservation of momentum. It's a really fundamental principle.
Conservation, meaning it stays the same.
Pretty much. It says that in a closed system, that's key, closed system, the total momentum before an interaction equals the total momentum after the interaction.
What's a closed system again?
It just means we're only considering the objects that are interacting with each other, and there are no significant external forces acting on them, like friction or air resistance are ignored or are very small.
Gotcha. So if things just interact among themselves, the total momentum doesn't change. The textbook had that whale example.
Yeah, the breaching whale. To jump up, it pushes water down. The whale gains upward momentum. The water gains downward momentum.
And they cancel out because of Newton's third law. It's equal and opposite.
Exactly. The total momentum of the whale plus water system stays 0, assuming it started at rest.
Okay, let's go back to the bat and ball. The ball's momentum changed hugely. What about the bat's momentum?
Good question. Newton's third law again. The ball pushes on the bat just as hard as the bat pushes on the ball for the same amount of time.
So the bat experiences an equal and opposite impulse.
It does. Its momentum changes by plus 12 kilojoules.
But the bat is way heavier, especially the batter holding it.
Right. So that change in momentum results in a tiny, almost unnoticeable change in the bat's velocity. The ball goes flying, the bat barely budges.
It's like that fly hitting a truck analogy again.
Pretty much. Or think about ice skaters. If one pushes the other,
and they start from rest, total momentum is 0.
Then after the push, one goes one way, the other goes the opposite way. Their individual momenta are equal and opposite.
So the total momentum is still 0, conserved.
You got it. Same idea with billiard balls colliding on a smooth table. It's a nearly closed system.
And there's that equation, right? MAVA initial plus MBVB initial.
Equals MAVA final plus MBVB final. Yeah. It just says total momentum before, total momentum after.
Okay, let's try the textbook examples. Ball A, 2 kilograms at 2 meters west. It's ball B, 4 kilograms at 1 meters west. Then ball A slows down to 1 meters west. What about ball B?
You'd plug everything into that equation. Initial momentum is 2 kilograms, 2 meters, plus 4 kilograms, 1 meters, all west. Final momentum is 2 kilogram, 1 meters, plus 4 kilograms ZB. You set them equal and solve for VB.
We won't do the arithmetic now, but that's the process. Cool. Example 2. Railroad car, 30,000 kilograms at 2.2 meters east, hits an identical stationary car, and they stick together.
Sticking together is a special case. It means their final velocities are the same. Let's call it V.
So the equation becomes MAVA plus MBVB equals MA plus MB times V.
Perfect. So 30,000 kilograms, 2.2 meters, plus 30,000 kilograms, 0 meters, plus 30,000 kilograms, plus 30,000 kilograms.
Okay, so 66,000 equals 60,000 times V. V must be 1.1 meters east. They move off together, but slower.
Yeah, those are great for visualizing this stuff. And they often let you look at energy, too, which brings us to the elastic versus inelastic collisions.
Okay, so momentum is always conserved in a closed system. But energy? Sometimes it is, sometimes it isn't.
That's the gist. In a perfectly elastic collision, both momentum and kinetic energy are conserved.
Kinetic energy being the energy of motion, 1/2 millV squared.
Right. Think of those ideal billiard balls again, or maybe steel ball bearings. They bounce off each other without losing much energy to, like, heat or sound.
But most real-world collisions aren't like that. They're inelastic.
Yeah, most everyday collisions are inelastic. Momentum is still conserved, always. but kinetic energy is not.
Where does the kinetic energy go?
It gets transformed into other forms, maybe potential energy if something gets bent or deformed, or maybe it's lost as heat due to friction, or sound energy like the crunch in a car crash.
So the car crash is definitely inelastic. Lots of sound, heat, bent metal.
Absolutely. A perfectly inelastic collision is when the objects stick together after hitting, like those railroad cars. That usually involves the maximum loss of kinetic energy while still conserving momentum, of course.
So in those bumper car simulations, the bouncy setting would be close to elastic.
Trying to be, yeah. Kinetic energy mostly conserved.
And the locking setting, where they stick together.
That's perfectly inelastic. You'd see a definite drop in the total kinetic energy after they collide, even though the total momentum stays constant.
Fascinating. Okay, momentum is conserved, kinetic energy sometimes isn't. Let's broaden the scope now to all forms of energy. The textbook uses a concert.
Yeah, it's a great example because so many energy forms are present. You've got the drummer using mechanical energy.
Muscles moving, sticks hitting drums. Got it.
Chemical energy stored in, well, the musicians' bodies from food,
Yeah.
maybe batteries powering effects pedals.
Electrical energy flowing through wires to power the lights and amps.
Those lights producing electromagnetic energy, visible light, but also infrared heat, which is thermal energy.
And obviously sound energy from the speakers and instruments. The textbook lists 7 types: mechanical, chemical, electrical, electromagnetic, thermal, sound, and nuclear.
Nuclear energy, yeah. The energy stored in the nucleus of atoms. Think nuclear power plants or the sun.
Okay, 7 types. And the really key idea is that energy changes form, right? Energy conversion.
Constantly. It never just appears or disappears. That's the law of conservation of energy. Energy can change from one form to another, but the total amount stays the same.
Like watching a movie with popcorn. The electricity.
Came from maybe burning coal, chemical, to make heat, thermal, to boil water and spin a turbine, mechanical, to generate electricity, electrical,
Which then goes to your popcorn machine, becomes thermal energy to heat the kernels.
which then explode, creating mechanical energy and sound energy. It's a chain reaction of conversions.
Very cool. The book also talks a lot about potential and kinetic energy conversion. The water slide example.
Classic example. At the top, you have gravitational potential energy because of your height.
Stored energy ready to go.
As you slide down, gravity pulls you, converting that potential energy into kinetic energy of motion. You speed up.
Faster and faster.
Yeah.
Then at the bottom, mostly kinetic, to get back up.
You have to use your muscles converting chemical energy into kinetic energy to climb the stairs, which increases your height and stores gravitational potential energy again.
It's a cycle, like swings on a playground or a pendulum.
Or trampoline. Stretching, it stores elastic potential energy, which then launches you up, giving you kinetic and gravitational potential energy. It's everywhere.
So all this energy changing forms. Where do we get it from originally? This leads to renewable and non-renewable sources, right?
Exactly. Non-renewable resources are those we use up much faster than they can form naturally. Fossil fuels are the big ones. Oil, coal, natural gas.
And uranium for nuclear power.
Right. Fossil fuels are basically stored solar energy from millions of years ago, trapped in ancient organisms. Burning them releases that energy.
But burning them also releases stuff we don't want, like pollution.
Unfortunately, yes. Carbon dioxide, which contributes to climate change. Sulfur dioxide causing acid rain. Nitrogen oxides making smog. Particulates. Natural gas burns cleanest. Coal, the dirtiest.
And oil has risks of spills, too. Nuclear doesn't have the air pollution, but
It produces radioactive waste, which is hard to dispose of safely, and there's always the risk, however small, of accidents. Plus, uranium itself is a limited resource.
okay, so those are the non-renewables. What about the good guys, the renewables?
Renewable resources are either replaced quickly or are practically limitless. Think wind, sunlight, moving water, biomass, and geothermal heat from inside the earth.
Generally cleaner, right?
Much lower pollution, generally. Though they have their own challenges like cost, land use, or intermittency. Currently, we use far less renewable energy than non-renewable.
Let's quickly run through them. Wind.
Wind turbines convert the kinetic energy of wind into electrical energy. Wind itself is caused by uneven heating from the sun. Drawbacks can be noise, visual impact, danger to birds.
Sunlight, solar energy.
Using solar panels to convert electromagnetic radiation directly into electricity, or using the heat for warming water or buildings. Limited by cloud cover and nighttime, obviously.
Moving water, hydropower.
Dams use the potential and kinetic energy of water stored behind them to turn turbines and generate electricity. Can disrupt river ecosystems, though.
Biomass. Sounds organic.
It is. Burning wood, crops, or waste for heat or electricity. Or converting crops like corn into biofuels like ethanol. Still produces CO2 when burned, and growing biomass crops takes land.
And geothermal. Heat from the earth.
Tapping into underground heat reservoirs to generate steam for electricity or for direct heating. High initial cost, but the energy source is basically free and constant once you're set up, limited to certain geographic areas.
Okay, so we have all these sources. How are we actually using energy, say, in the US?
Well, the textbook data shows we rely heavily on non-renewables. Oil is the biggest chunk, then natural gas, then coal. Renewables are a much smaller slice of the pie.
And the US uses a lot of energy per person compared to other places.
Quite a bit more, yeah. And since most of that is fossil fuels, it links back to higher pollution levels.
Which brings us to the idea of energy conservation. Using less, basically.
Using less or using it more efficiently, both count. It's about reducing our demand, especially for non-renewable resources.
The book had tips, right? Like for transportation?
Yeah, simple things. Plan trips to combine errands, use public transport or carpool when possible, choose fuel-efficient vehicles, bike or walk for short distances. It all adds up.
And at home.
Turning off lights and appliances when not in use, switching to energy-efficient LED bulbs and appliances. Look for that Energy Star label adjusting your thermostat a few degrees, ceiling drafts. Lots of small actions make a difference.
So wrapping this all up, we've gone from momentum, the oomph of moving objects and impulse, the force over time that changes it.
Through the crunch of collision, seeing how momentum is always conserved, but kinetic energy might take a different path in inelastic crashes.
Then we explored all the different flavors of energy, mechanical, thermal, chemical, all that, and how they transform constantly following the conservation of energy law.
Especially that dance between potential and kinetic energy we see everywhere, from water slides to bouncing balls.
And finally, we looked at where we get our energy, the difference between non-renewable sources like fossil fuels and the more sustainable renewable options, and why conserving energy matters.
It really connects back to that mission, right? Understanding the physics in motion all around us. These aren't just abstract ideas. They govern how cars work, how athletes move, how power plants function, even how planets orbit.
Yeah, you start seeing it everywhere once you look. Like spotting the physics engine running the universe, or at least your favorite game.
Exactly. It's the underlying rule set.
So here's something to think about. Now that you have this deeper understanding of momentum, energy, and how they interact, how might these principles shape, future technology? Or maybe help us tackle those big energy challenges?
Definitely something to chew on.
And with that thought, we have to say, this deep dive into motion and energy was brought to you by the Geeky Gamer Science Teacher. Thanks for sharing your passion for physics.